Hi, everybody. Welcome to the Penn State Technology Club. Tonight, our guest is Erick, and I hope I don't butcher this, Galinkin. Um, and he will be talking about vulnerabilities in my machine learning. It's more likely than you think. I hope I did that justice.
No, that was perfect. That was great. And you did pronounce my last name correctly. So
Perfect.
yeah, that was beautiful. Thank you so much, Ray. And I'm going to share my screen. And I am also sharing sound. There's a video at one point that does happen to contain some strong language. Nothing too horrific. But if strong language is bothersome, we can skip it, or you can just mute while I play the video. So yeah, as Ray said, tonight I'm talking about vulnerabilities in my machine learning. It's more likely than you think. This is a very old meme. It's so old, and if you get it, I'm so sorry. So this is me. This is a picture of me in case you can't see my face because you have the slides full screened, which is probably a good choice. During my day job, I do AI research at Rapid7. I also do a bunch of other stuff. So please, be impressed and tell me how impressed you are. Not on here because it just happened today is I also took a research position with the Montreal AI Ethics Institute. So I think a lot about artificial intelligence and ways that it could go wrong. And so to kind of get to it is like, what is machine learning, right? There's a lot of conversation about machine learning. There's a lot of conversation about artificial intelligence. And so I think it's prudent to start with a definition of machine learning. And this is a definition of machine learning that is true and does work. If you want your stonks to go up, you can use machine learning and get all of that sweet, sweet venture capital. That's not the definition that we're going to use tonight, though. Tonight, we're going to set out 3 terms up front, and I'll fill in. If at any point I gloss over something, I assume too much, there's something confusing, please drop a question in chat or, feel free to interrupt me. So first definition, artificial intelligence is the branch of computer science that deals with automated decision-making. Machine learning is the subfield thereof, where an agent learns, right, whether it's via direct interaction with an environment or through formatted data, some function that allows it to map the inputs it gets to the outputs that you want. And there's some nuance there, but this is kind of the loosest definition I could give. And a vulnerability. So a vulnerability is any software bug that you can use to make software do something that it's not supposed to. So you can leak information from it. You can make it execute arbitrary code for you. There are lots and lots of vulnerabilities. Not all bugs are vulnerabilities. Some people might argue that this definition is too broad because not all vulnerabilities are exploitable, but I don't care, and I use this definition because it makes sense. So the caveat I want to put up front is that these are just a small sample of vulnerabilities that affect machine learning. And there are at least 2 things that I'm talking about that some people might argue are not actually vulnerabilities in machine learning or vulnerabilities that affect machine learning. But I think they're important, and so I want to talk to you about them. So the first thing I want to talk about is neural networks. And a lot of people have heard of neural networks. There's a lot of conversation about deep learning and neural networks broadly. And to kind of do it justice would take a lot more than the time that we have, even if I took the whole 30 minutes to an hour. We could be here all night. So the initial inspiration of neural networks was the brain, right? If you look at a diagram of an axon and dendrites and synapses, you'll kind of see an architecture that looks very similar to artificial neurons. Neural networks are very, very, very good at computer vision and natural language processing. All of the benchmarks in both of those fields, all of the state-of-the-art results in both of those fields are currently held by neural networks. There may be some exception to that, but any exception to that is probably some really old or esoteric benchmark that people don't care that much about, right? The real benchmarks people work on in the field are all held by neural networks in those two fields. And so people want to apply them broadly. So the way that neural networks work in a little bit more than a minute is you get some input to your network, and there is some matrix multiplication and a nonlinear, right? So different than y equals mx plus b activation function that feeds to the next layer and the next layer and the next layer. And eventually you get some output. And then depending on what loss function you specify, you get an error, right? So if your output, say it's a binary classifier, is 1 or 0, and at your last neuron, you output 0.79, and the class is equal to 1, then you have a mean squared error of 1 minus 0.79 squared, which I'm not going to bore you to death with at the moment. And then that error gets backpropagated through the network. And backpropagation is the result of taking that error and doing a directional derivative, the vector value derivative of the network. So that is the gradient of the loss function at each layer. And then feeding that error back through the network. The weights are adjusted according to that gradient, right? They're either increased or decreased. And that is how a network learns. And iteratively, the predictions get better as it minimizes that loss function. And if you have done a good job and if you have a good data set, caveats, you end up with a very good classifier. You can also use neural networks for regression, and you can kind of use them for clustering. Classification, regression, and clustering are three of the most common tasks in machine learning. Classification and regression are what's called a supervised learning task, where you have data and labels, and you try and find something that maps your data to your labels. And clustering is what's called unsupervised learning, where you don't know the labels and you try and sort things into classes based on their properties. So that is a super quick crash course in neural networks. There's another category of machine learning that we'll talk about later as well. So to get into vulnerabilities in neural networks, the first one that I want to talk about is kind of the most banal, but it is a real vulnerability. And that is bias poisoning or neural backdoors. Neural backdoors sounds a lot scarier, but it's a really simple attack. So if you have access to the model, right, you have gotten access to the system the model is hosted on, you've phished credentials, whatever uh, method you have gotten unauthorized access as a bad guy to the model itself. What you can do is you can make the classifier output whatever class you want. So if this is like a facial recognition system, right, that you use for badging, and it looks at your face and it says, is this person an employee? You can make every face evaluate to be an employee by doing bias poisoning. And essentially the way that you would do that is, if you look at this diagram here on the right, we have these two output neurons. And let's say that the neuron number one is employee and neuron number two is not employee. Realistically, this would work better if it were a single neuron with a sigmoid output, but those are details that we're going to not care about at the moment. So what you could do is you could make the bias, right? So thinking about our, back to what, ninth grade, y equals mx plus b, right? So you have your weight matrix, and that's your m, that's the slope. X is your input, and that b is your bias vector. So what you can do is you can make that bias really, really, really big. And then no matter what input you get, your bias will force it into the positive class. Or you can make your bias really, really, really negative, and then you can weigh it always into the negative class. And so this is one of the sort of most banal vulnerabilities, but it's something that people don't really think about, right? And that's really what I want to get at throughout this whole thing, is that a lot of people, both security professionals and data scientists, don't think about it, because to a lot of security professionals, this is some weird, magic box that you input data and you output decisions, and it's scary and I don't understand it. It's all sorcery. And data scientists, machine learning engineers are often so focused on optimizing for whatever outcome they need, whether that's accuracy or robustness, that thinking about how the model gets secured post-deployment is not a major factor. And so doing things like auditing the weights or auditing the model itself doesn't tend to come up in discussions about threat models. And so even though this attack is kind of banal, it can have major effects because it tends to just slip through the cracks. And so the next attack I want to talk about is what's called a model dumping attack, or a model theft attack. And kind of the idea of model theft is that training data can be difficult to acquire, and models can be very expensive to train. And so maybe you just want to steal one, right? Maybe you just want to have a model that somebody else has trained. Super plausible. I definitely have had cases where I wished I didn't have to train and tune a model, and I could just steal one, but I can't. Mostly because that's intellectual property theft, and I work for a company that would fire me if I did IP theft. That's kind of a joke. So one of the great examples of this is Will Pearce, who is a colleague of mine. He's not at Rapid7. He was at Silent Break Security. He's a phenomenal red teamer, right? He's not even a machine learning engineer or an AI researcher. He's just a hacker, just. He discovered this CVE 2019-2634, which is actually one of the first CVEs issued for like this kind of a vulnerability, where it is strictly a vulnerability that impacts the machine learning itself. It's not remote code execution in a machine learning library. It's not data leakage from a machine learning library. It's an actual attack against the algorithm. And I think that's really cool. And essentially, the way that he did it is he would send a bunch of emails to this Proofpoint email security appliance, and sending email after email after email after email, he got all of these response headers. And so he was able to kind of pick what words would allow the model to output different things, right? And so eventually he ended up with this scored data set that correlated emails to maliciousness scores. And he used that to create a copycat classifier. So a copy of Proofpoint's model without knowing anything about the inner workings of the model, just based on giving it inputs and outputs. He was able to reliably predict what the model would predict. So even though the individual weights may not be the same, the actual architecture may not be the same, it is a functional equivalent. And that's really cool. It's really cool and it's really scary because, once again, when we deploy our models, we expect to want to have very high availability. We want to have really high uptime. And if we're getting a bunch of requests, what we want to do is we want to scale to handle those requests. So if we scale to handle those requests and we're returning enough detail in our output, we can actually make ourselves vulnerable to this kind of attack. So it's really cool. And this gets to a point that I will make a little bit later about adversarial examples. And by adversarial examples later, I mean, I'm going to start talking about adversarial examples, and then we're going to circle back to the Proofpoint theft. So adversarial examples are really, really cool. This little GIF on the right is from a really well-known paper in the adversarial machine learning space, where they 3D printed that turtle. And Google Cloud Vision, which is an extremely well-respected, well-known commercial computer vision product, right? Like, I think everybody on the call knows about Google. And I'm sure that anybody who's watching on YouTube, by the way, hi, if you're watching on YouTube, has heard of Google. If you're watching on YouTube, YouTube is owned by Google. So there you go. They 3D printed this turtle that is very obviously a turtle to any one of us who is looking. And the way that it is printed is so that it does something, it contains what's called an adversarial perturbation. And so by adding a little bit of noise to the image, or in this case, adding some details to the turtle, right? Some of that noise, how there's like, if you look at its back, it's not quite perfect. There's some little weirdness. There's some like red dots, but it doesn't look anything like a rifle. They got this to reliably classify this turtle as a rifle. And so it is commonly called the turtle rifle paper, even by people who've read it like 30 times and should know the title. We still call it the turtle rifle paper. And so the idea is that these are imperceptible to humans. Any reasonable human being who was asked what that object was would say that it's a turtle. It's a toy turtle. I have a 3-year-old upstairs who I could ask, and he would tell me it's a turtle. Nobody would say that that's a rifle. And yet Google Cloud Vision misclassified it as a rifle. And they did fix it, but there are adversarial examples in any computer vision system. And so where this gets scary is when you have 3D printed adversarial examples, and you think about things like self-driving cars. the self-driving cars potentially misclassifying objects on the road or things, you know, stickers placed on stop signs has been an example used. Um, that can have real world impacts and potentially disastrous impacts. So these are real threats that we need to think about and we need to work to mitigate. Unfortunately, a lot of the defenses against adversarial examples are not very good. Um, Nick Carlini, who is probably he is definitely one of the foremost researchers in this space, um, went through all of the defenses presented against adversarial examples at NeurIPS 2018 and showed that the only thing that is effective universally is training against adversarial examples. So you generate adversarial examples and train against them. And so to bring it to the security space, the possibility of developing adversarial examples to bypass malware detection is not just hypothetically real. It's something that has happened. So one of the earlier papers by Biggio et al. Appended sections to malicious PDFs to get them to be classified as benign, using the same sorts of techniques that are used to generate adversarial examples in computer vision. In 2019, which I think based on 2020 adjusted time was 38 years ago, a bunch of benign strings were appended to bypass Cylance universally. And so if we can dump models like in the proof pudding attack, what Will did that to follow up on that model dumping is he used that copycat model to test whether or not phishing emails would get caught. And so if you can dump a model and then you can develop examples that bypass that model, well, then you don't have any security. So your machine learning powered security is only as good as the defenses that you have in your machine learning algorithm. Everybody on YouTube is missing out on the banter in chat. Okay, so this is my big caveat. These aren't per se machine learning vulnerabilities. They are vulnerabilities that relate to machine learning. But they're cool, and I'm going to talk about them anyway, because they're close enough. So before we get into the first one, I want to cover reinforcement learning, which is that third class of machine learning that I mentioned up front. And so the easiest example of reinforcement learning is thinking about a Roomba, right? If you have a Roomba, it doesn't usually get kicked by a cat to go somewhere else. It bumps into a wall, and then it turns, and it bumps into the wall, and then it turns, and then it keeps going, right? And if you have the really, really expensive Roomba, it learns a map of your house. So over time, it builds knowledge about which ways it should start going. And that's only if you have the Roomba that I can't afford. But I have friends who have them and they're really cool, and their docking station empties their little vacuum container. It's great. Another really well-known example is AlphaGo was reinforcement learning powered. AlphaGo was developed by DeepMind and learned how to play the game of Go, which is a very ancient game that originated in East Asia. and it defeated the best player in the world, Lee Sedol. There's a whole documentary on Netflix. If you're interested, it's really, really cool. It's really, really accessible. And they get really good at Atari games, and there are some reinforcement learning fails where people write bad reward functions, but essentially based on whatever environment you put it in, it interacts with that environment, it gets feedback, and it tries to optimize whatever your reward function is. So one common thing that happens is you have a reward of 0 for failure and a reward of 1 for success. And when it gets that success reward, it learns that the things that it did in that iteration were good. In some cases where you want things to accomplish a task very quickly, you might have it at every time step get a small negative reward. If you've watched Rick and Morty, it's like a meeseeks. Being alive is pain to a meeseeks. And so it wants to accomplish its task as fast as possible so it can die. That is exactly how reinforcement learning agents can be programmed to behave if you give them a negative reward at each time step. The longer it's alive, the more pain it feels, and so it wants to accomplish the task as fast as possible. And so where this comes into security is that Hiram Anderson and a bunch of other phenomenal researchers at former Endgame, now Elastic, although Hiram is now at Microsoft. Bobby Fillar is on this paper as well. Somebody important who I'm missing who's going to yell at me if they watch this, but they're not on the call. So somebody will have to look up the paper and let them know that I forgot them. It's not Bobby and it's not Hiram. Phil Roth. Now he can't get mad at me. There are 2 other people on the paper whose names I don't remember. Anyway, they used reinforcement learning to evade malware detection. And so they framed it as a game, the exact same way that OpenAI frames their Markov decision processes to play Atari games, to play StarCraft, and so on. And so, excuse me. In the game, the malware sample is modified and passed to an anti-malware agent or an anti-malware engine, and then a reward of 0 if the malware was detected, or a reward of R, they used 10 in this paper, is given if it evades detection. And then that is fed back into the agent where the malware is modified and then sent back to the anti-malware agent, and it learns to keep evading these machine learning powered detectors. So it was a really cool use of machine learning and security, and in particular of reinforcement learning. In the machine learning community, reinforcement learning is very often viewed as a toy. Even people who have dedicated their lives to reinforcement learning research say that it doesn't work. And so it's really cool to have a very practical application of reinforcement learning, especially in the security space. And so the other machine learning powered kind of vulnerability, it's kind of a machine learning powered attack, is deepfakes. And deepfakes are, as you could probably read on the slide, they're images that are created that purport to be real. They seem to be one thing. They're often based on images or videos of real people, but they're completely synthetic. They're generated, right? And so in nefarious purposes, right, the way that they've been used in a security context is we've seen them used for phishing, where it does kind of a style transfer. It learns the style of writing that people use. It's been used a lot in sextortion scams, where people generate deep fake pornography of people and threaten to release it unless they pay some kind of ransom, which is genuinely horrific. It's been used for blackmail. It's been used for basically all of the worst things you can think of. It's also been used to put Nick Cage into movies that he's not in, which is funny and benign. And they're really hard to detect. And so I'm going to play this video. It does contain some strong language. If that is upsetting to you, it's 2 minutes long, so you can just mute your audio, or if you're watching on YouTube, skip 2 minutes. But I think this is really cool, so I'm going to play it. Please let me know if you have trouble hearing.
We're entering an era in which our enemies can make it look like anyone is saying anything at any point in time, even if they would never say those things. So, for instance, they could have me say things like, I don't know, Killmonger was right, or Ben Carson is in the sunken place, or, how about this, simply, President Trump is a total and complete dipshit. Now, you see, I would never say these things, at least not in a public address, but someone else would. Someone like Jordan Peele. This is a dangerous time. Moving forward, we need to be more vigilant with what we trust from the internet. That's a time when we need to rely on trusted news sources. It may sound basic, but how we move forward in the age of information is going to be the difference between whether we survive or whether we become some kind of fucked up dystopia. Thank you, and stay woke, bitches.
So, right, if you're just watching that, if you just encounter that video out in the world, it might not be obvious to you that that's fake, right? I mean, we can expect that that particular video is fake. But something just a little bit more plausible, it would be really hard to detect as a human observer. And these are very similar to those adversarial examples. They're generated in very similar ways to be convincing. And that's what's so nefarious about them, is if someone shows you a video that looks and sounds like someone saying something that's only a little bit more extreme, or maybe they got caught on a hot mic, that could be really damaging, and that could be really scary. And you can see how these can be used for phishing, and these can be used for extortion and blackmail. And I talk about that a little bit here. It takes advantage of that same adversarial example type thing. Are they a machine learning vulnerability? Not strictly speaking, but they're a vulnerability in kind of human perception. And it's really risky. And the fact that we as people are not good at detecting deep fakes, especially when they reinforce our biases. And also, machines are not very good at detecting deep fakes, makes this a really important problem that is getting some attention, right? Kaggle is a machine learning data science competition organization. They launched a deepfake detection challenge. There are quite a few efforts on deepfake detection, but it's hard. It's a really hard problem. And the next, bring it back to actual vulnerabilities in machine learning algorithms. I want to talk about model inversion, which is my personal favorite topic because it's one that I work on. And this kind of is the step ahead of adversarial examples. So what we see on the right here, down at the bottom are ground truth images. These are from the Celeb-A data set, which is a facial recognition data set. And then on above, you see all of these examples generated by generative adversarial networks, which are built on the same principles as adversarial machine learning. And the goal of these networks is to recover the ground truth images. And there are a few defenses applied here, and I'm not going to talk in depth about the defenses applied because it's kind of abstract and really boring. But if we look just specifically at the ground truth images and the no defense images, you can see that, it does a pretty good job. They're not perfect copies, but you can get a good idea of what the original image looked like. And now on facial recognition, that's really something. But if we start thinking about all of the other things that people put into machine learning models, medical imaging, financial records, personally identifiable information, the fact that we can get really, really close to recovering those things means that if your network has learned any sensitive information, it could be at risk if you aren't applying any defenses. And that's really scary because this is really early research, like this year. I think that this particular paper came out this month, or no, it's June now, last month. So, we're still in the early days of these attacks. And if history is any guide, these attacks are only going to get better. So kind of more on the vulnerabilities in machine learning frameworks side of things. There was a paper put out in 2017 that's gotten very little attention that used fuzzing, just a fuzzer. It's AFL, American Fuzzy Lop, which is a very common fuzzing library, to just look for bugs in machine learning frameworks. And this was just done by, a handful of interested academics. And they found 5 vulnerabilities in OpenCV, which is a very common computer vision library, 3 in the malheuristic application, and 1 in scikit-learn, which is one of the most popular machine learning libraries out there. And a lot of this stems from the fact that these are typically open source projects. And these are open source projects that are all written by machine learning engineers and data scientists and people in the computer vision and machine learning community. They're not written by people who always follow secure development practices or even know what memory safe methods are. They don't necessarily account for things like null pointer dereferences or other common vulnerabilities, right? Use after freeze are not something that data scientists are used to looking for. And so, again, this kind of gets back to the fact that we really need to be thinking about this as a potential attack surface. We need to be thinking about these models because these models are often accepting input in completely unvalidated ways from completely untrusted sources. And the theory is, well, it just goes into the magic machine learning box and something comes out, and how could code get executed? And it turns out, right, in this Stevens paper, it can, and it does. And that's really worrisome. So, that's really all I had. These are the references. If you are interested in these references, if you're interested in these slides, I can get you a copy. You can feel free to reach out to me on Twitter, LinkedIn, email. I use my whole real name everywhere. I'm very easy to find. I might be the only Erick Galinkin. And that's all I had tonight. So thank you all for joining. If you have any questions, please feel free to ask.
Anybody have any questions? Last call. Oh, there's
We
one
do
in
have
chat.
one. Do you feel people will start using deepfakes as an excuse for bad press? Absolutely. Oh yeah, for sure. I mean, irrespective of what your opinion is of the President of the United States, he has definitely used the term fake news, which relates to sort of discredit negative coverage, right? Using deepfakes as an excuse for bad press is absolutely something that could come out, right? I mean, we've seen that doctored video of Nancy Pelosi, which was not a deep fake, but it could have been. And if it had been, it might have been more convincing to more people. And I'm sure that if she had said it was a deep fake, there would have been a non-zero number of people who believed it was an excuse for bad press. And I definitely think that once we see deep fakes used to make people look bad, we will see people use it as an excuse for actual things that happen to discredit them. And I hope that we'll catch up to detecting deep fakes. But right now they're really hard to detect. They're really hard to detect systematically. And, as you could kind of see in that video, they're hard to detect by people, right? Like at first it felt like that was a real video. Yes, that is exactly right. People believe all kinds of things. And saying that something is a deep fake or suggesting that something is a deep fake is a very convenient way to give people with confirmation bias an excuse, because they'll say, well, prove it isn't a deep fake. You can't. It's hard. Yeah. Anybody else? Does manipulating Google Translate results fall under here? Yes. Yeah, it does. Yeah. So that's something I didn't talk about. And I didn't talk about it because I have a religious position on it, which is data poisoning. And data poisoning is a very real thing. And that's exactly what manipulating Google Translate results falls under. And so data poisoning is when you manipulate a data set such that you change the outcome of a classifier that relies on that data set. And data poisoning, the difficulty with data poisoning is you might also just have a crappy pipeline, or you might also just be ingesting like garbage data, you know, and it's hard to tell whether it is an on purpose manipulation of your system versus just a bad data pipeline. But it definitely falls under machine learning vulnerabilities as a broad umbrella.
I think there was one other question in the chat. Where did it go?
Oh, why does reinforcement learning have so many dissenters? Reinforcement learning has a lot of dissenters because I think that it's because so many of the applications of deep learning are literally games. And so it doesn't feel like science, right? If you have a computer vision system and you say this can recognize 100 classes or 1,000 classes of objects based on a photograph, right? Or it can help you drive a car. It knows how fast it's going. Or you have a natural language processing system that can automatically tell you whether a review on Amazon is positive or negative, without you having to read it, right? Or you have, 1,000,001 other applications of machine learning. Those feel very tangible. Those feel like real progress in the world, and you can see the benefit to humanity. The things that reinforcement learning has done really well on is like it's gotten the all-time high score on Qbert. It has beaten every human record ever set in Space Invaders. It is very good at Atari games. It is good at StarCraft. Like it's good at playing video games. Those are most of the things that have been used in reinforcement learning. And so to a lot of people, it still feels like a toy, right? It's a parlor trick. And the other thing is it doesn't always work. So you can run the exact same algorithm on the exact same environment and get much, much worse results the next time, right? The results aren't always repeatable because there's some randomness. It suffers from what's called the exploration-exploitation dilemma, which is, do I keep trying random things to get a better result, or do I just do the one thing I know gets me some kind of positive reward? And so, if I have a system and I run it 3 different times and I get 3 wildly divergent results, I'm probably not going to believe very strongly in that system. You're welcome.
Any other questions before we wrap up?
Would you say there's a more vulnerable type of ML model? That's not a fair question. Yes and no. So I will say that quantifying vulnerability to say more or less vulnerable is very, very difficult, and it's not really something you can do. I will say that neural networks have a wide variety of vulnerabilities and have widely been studied as attack surfaces. I will say that it is easier to find vulnerabilities in machine learning models that are differentiable, right? That have a derivative, especially if they are differentiable everywhere. If they're, if they're differentiable everywhere, if they're smooth, that makes them much, much easier to find vulnerabilities in, because you can always find some point, some right inflection point, where you can push things to the other side of the classifier, and you can always compute the distance that you need to move one point to get it to the other side of the decision boundary. So linear and logistic regression are smooth. And so you can always know exactly how far you have to move something to get it to the other side of the decision boundary. And if that is small enough, then that's where you get those adversarial examples. But neural networks are the right combination of very complex and differentiable. And so they tend to have more vulnerabilities than other models. Yeah, nobody tries to find adversarial examples on decision trees because there's no gradient on a decision tree. And so it's really hard. That's not true. Some people do, but they have to work really hard to find them. They can't just compute a gradient. I think we have time for one more if anybody else has a question. Otherwise, I can just talk forever. This is my favorite thing.
How has your week been?
My week's been not great. It's not been great. Today is the best day this week. I've been really busy. Just a lot of things going on. Yeah. Oh, that's a real downer. That's a real bummer. Oh, but I did get this. I got an iPad Pro with the little keyboard, and it's got the little trackpad. Strongly recommend it. Very, very impressed. I'll never, ever buy a laptop again. I'll never buy another laptop. This does everything I need it to. It's great. I really recommend it. Better battery life, more portable, looks cool. Yeah, of course I've got the pencil. Gotta have the pencil. The pencil is real good. Strongly recommend it. You can highlight papers, you can take notes. It's great. And the keyboard is even better than the last generation MacBook Pro keyboard. So yeah, that came today. That's why today was the best day.
Getting things in the mail always makes the day better.
That's true. That's the only good part of COVID is instead of going to the store once at the weekend, I just get like little presents every day. It's pretty cool.
Yeah, I find myself ordering like towels, just like inane things so they come in the mail.
Mm-hmm. Yeah. Or your delivery gets split up into a bunch of orders, and so it comes over the course of like a week and a half. Anyway, I think we're officially on a tangent.
All right. Well, thank you for talking with us tonight, Eric. It has been great. And everybody have a good night.
Thanks, everyone.
Thanks.